All right. Welcome, folks. So we've been talking about induction machines in the past couple of videos, and today we are going to look at induction machine speed control techniques. Okay. Typically, in applications in industry, induction machines are used primarily for speed control, for conveyor belts, for escalators, and all that. They are typically under some form of control, primarily used for speed control, for pumps, fans, and such applications. There are torque control applications, but few and far apart. So in controlling speed, there are several different techniques that are available for us to control. Some of them are very efficient. Some of them are not that efficient, but very simple and cheap to implement. So depending on application, you will want to consider what technique or technology you want to use. Okay, so we'll actually get right into it. First of all, is the line voltage control. This is a very crude mechanism to control the speed of the machine. And what we typically, first of all, we want to notice is when we change the rated voltage applied to the machine, okay, when we change the voltage. So let's say you have a three-phase set of windings, right? So you're going to have three-phase set of windings like that. You can change the voltage that you apply to a phase, okay? And we're going to maintain the balance. Instead of applying, let's say this is rated for 240 volts DC each phase, right? And then we're going to change, instead of 240, we're going to apply 50 volts to each phase. And when we do that, what happens is, in the torque speed curve, that curve will shrink. Okay, it'll shrink. So this can be used to control speed, at least in a crude way. Okay, now if you think of the torque curve, or the torque speed curve of a load, okay, the load and the motor works together. All right, the function of the torque, the load torque, will depend on the speed. It's proportional to a certain power of speed of the fan. Okay, so you're going to have a motor, right, and then you're going to have a fan coupled, and if the fan rotates very fast, the load torque will increase and the induction motor will have to follow, right? So that's kind of the idea behind this curve. As with speed, that load curve will change. Now, by controlling voltage, let's say you want to provide less volume of air, right? Less volume of air from that fan, then you can decrease the voltage. And when you decrease the voltage, what will happen is the torque speed curve will be shrunk down to this level, and this new intersection point of the load curve and the motor curve is somewhere around there, right? So the speed has dropped and the load has dropped. Okay, so what's happening is we're kind of dropping the load, which inherently drops because we change the speed. So the amount of air volume that you have to move has reduced, and therefore the speed has changed. Okay, and as you get closer to the synchronous speed, it gets much more finer in terms of how much control you have. Because your resolution kind of decreases, right? Because they're very tight, close to this point. Okay, so by controlling line voltage, you can control the speed, but it's not. It applies to certain applications, but not a whole lot of them. And changing rotor resistance is another option, but for that you need to have access to the rotor windings. Okay, so if it's a wound rotor, if it's a squirrel cage motor, this is a little bit of a difficult task because you don't have access to the rotor bars, right? The resistance on the rotor bars, right? So if it's like that, you cannot control the resistance. But if it's a wound rotor, which means you have a set of windings similar to the stator on the rotor, and you have the ends open, you have the three windings from the rotor extended, right? And then you have slip rings, because as the rotor rotates, those winding connections have to follow. So they use slip rings to have that contact outside. If you do that, if you can have that, now you can place a resistance and you can adjust those resistances, right? So it's basically three resistances that you can adjust on the three phases. You can increase and decrease. Okay, by doing that, this becomes interesting. What will happen is, for that rated voltage without changing anything else, now you can shift you can kind of push your torque speed curve towards the y-axis, to the torque axis. Okay, so with the larger resistance, you are kind of increasing the total resistance in the rotor. Therefore, it's at a very large slant. So by doing that, now you can move, right, for the same torque. By changing resistance, you can move to different operating speeds. So let me try to draw that. If I draw, so let's say, for example, I want this torque, let's call it 1 Newton meter, just an example, 1 Newton meter, right? So if I want 1 Newton meter at this speed, right, I will set it to R4, the rotor resistance. I want 1 Newton meter at this speed, I will set it to R3, right? If I want to go all the way to full speed, I will set it to R1, right? So now by adjusting that state rotor resistance, you can control where you are at. So this is a little bit better method than the voltage control, but we need a wound rotor, okay, which tends to be a little bit more expensive in some cases, right? Okay, so now, so we talked about voltage control, we talked about the rotor resistance control. This is V over F control, very simple but effective. Instead of only controlling the voltage, we are controlling voltage and frequency, the ratio. So both voltage and frequency are scaled linearly or together, so that this V over F remains constant. Okay, so what happens is, so this is just a plot of how they are changed. Your voltage and frequency, they are being changed linearly, and then once they reach the rated value, they are held constant. Okay, and you can see that at different V over F values, what happens to the torque speed curve? It kind of moves as well as shrinks. Okay, so we can use this to achieve different torque speed points based on the application. Now, what tend to happen is, you can see that torque is dropping at the low speed ends because we are dropping voltage too, right? But ideally, the motor should or can achieve full torque, and it should be able to achieve that same kind of torque at this low frequency end. If you think of it, the torque is related to the current, right? It's proportional to current that builds the flux, and speed depends on the voltage in a more crude sense, right? So if you want to achieve these low speed points, and we should technically be able to do that, because current depends, if you try to think, okay, so can we really achieve that current? That comes down to the conductors that you use inside the motor, the windings, right? How much current can the conductor carry? Okay, so that means even at low speed, which means we are at a lower frequency or lower voltage, we can still pass the same amount of current through the conductor. That means we should be able to reach that rated torque for the motor. Let's say it's around here, right? So we should be able to achieve that. Therefore, we need to think, okay, having how can we improve or enhance the torque capability at low speed? Okay, so what the scientists or engineers did was, okay, why not boost the voltage? Okay, instead of having it uh, like that, they added a voltage. They boosted. So it's called we have control with voltage boost. And now we have really good performance. We have torque capability across all speeds. So if this is the desired torque, now by adjusting that VORF, we can achieve different speeds at the same torque. Okay, so now we can control the torque and speed. So this is very desirable, very practical. Okay, and still this is an open loop technique, and people use inverters to achieve this, to achieve V over F control. Right. All right, folks. So that's a little bit of an overview of speed control methods with induction machines. Of course, there are other advanced methods that you can use for torque control, field-oriented control, direct torque control techniques, indirect torque control, indirect field-oriented control, which relies on sensors and some kind of estimation of flux or current, to achieve control of the machine. Okay, I won't go into that details in this video, but just to give all of you an idea of how these torque speed curves work and then how they can be changed to achieve certain type of control was the only goal of this video. Okay, all right, folks. Thank you, and I'll see you in another video.